I'm just joking. If I can't answer, then I'll do my best. All right. So I'm Ryan Bodenstein. I have been working in the accelerator field for 22 years. Lucky for all of you, this is the only time I can give this talk where I can say it's literally been half my life. So half my life in the accelerator field. And now I get to share with you my current love, CEBAF. So you're all sitting over here, right? The accelerator site over here. Has anyone been on site? A good handful of you. Okay. So most of my day is spent in the machine control center right here. I'm there pretty much every day, partially because I'm helping with operation support, partially because I don't have an office anymore. But that's another whole story. So anyway, I'm going to be cracking jokes this whole time because it's right after lunch and I know everyone's going to be sleepy. So I'm going to make sure you stay awake. So let's get going through. Oops. There we go. So again, this machine is about 40 years old. And when it started off, it was a hole in the ground. Does anyone know what the sea level is in most of Newport News? Water table? Say what?
-5 feet or something.
6 feet. Yeah, there you go. So the tunnel floor is 30 feet. So we decided to build this accelerator not only in a swamp, but underwater, right? Because why not? So it is a pretty interesting little fact. It's built on the Yorktown Formation. So there is like a seabed, an ancient seabed that they built it on as the foundation, but it is technically underwater. So if you're in the tunnel, you're technically underwater. So hold your breath, right? I'm joking. So anyway, here's a brief overview, right? We start at the injector. Let's see if this works around here. We send it through a pair of cryo modules and we fold them over a bunch of times. This isn't a ring. This isn't a pure LINAC. This is a recirculating linear accelerator. So it combines elements of both, which also means it is a different beast to operate than a ring or a LINAC. Some parts are easier, some parts are far, far harder. And so in general, this is a very unique facility. There's not really many of these in the world, and we were kind of the first big one. One of the cool things that you all probably already know is that our experimental halls can take various energies depending on the number of times that the beam goes around. Except for Hall D, they always get top energy. They're special. But everyone else can adjust. So if they want first pass in Hall A and third pass in Hall B and fifth pass in Hall C, we can make that happen, right? So it all depends on how we separate things out and how we send them to the different halls. And I'll get to that. I'm just giving you the general gist first. But that's the idea. There's a lot of different ways that we can set up different energies to the different halls. Now this, assuming it still works, is a little bit of a cartoon that took way too long to make. But essentially, the beam will go around and it starts on the topmost arc, which here on the left seems to be spread out horizontally, but in reality, they are stacked vertically. I'll get into that in a little bit as well. But essentially, we can extract the beam at any of these passes as it goes around and send them to whichever hall is requesting that beam. And this is a continuous beam, so that would be a single macro particle going around. But the reality is we are a CW machine, which means every part of that RF wave is filled. Every bucket is filled. And so we send beam nonstop around the machine. Here's a wonderful engineering drawing. Boring, I know, but there's a reason I'm showing it, and it has to do with how these slides are laid out. It's actually pretty clever, and I can't take credit for it. It was actually one of the operators that laid out most of these. So first, you see the general overview. So we have our injector here, right? North LINAC, South LINAC, East Arc, West Arc, A, B, C, and D is over there. So what you're going to notice as we walk through is there's an overview over here, and it's showing you what you're looking at in this corner. So this is the injector line. This is, of course, a zoomed in part. Again, I know it's boring, but hang on, because we have photos, right? So we're taking a tour, and we're starting where the beam starts, right in the injector. Now, another cool thing, not only will you notice where you're standing, but you're looking at where you're looking. So this green is this picture. You see the green border. And this red one is showing you where you're standing to get that look. So as I'm clicking through these slides, pay attention, because that way you could pretend like you're really standing there looking at the different components of the machine. So what do we have here? Well, this is the very start. So this is essentially the gun, right? This is where the the electrons start, right? So there's a laser chamber in here, and the laser light comes through and hits a cathode here, and they send the beams out that way. And so in this white area is where the actual laser starts, right? And that determines the shape and structure of the beam, right? So the laser pulses 1, 2, 3, 4 for 4 halls, 1, 2, 3 for 3 halls. Those laser light then, as we all know, Einstein, right? You get your electron cloud off of this, and then we capture that and accelerate it through. And that's what's happening here. As we move down the line, oh, no, we're not moving down the line yet. I lied. This is the inner working. So this is more of what's actually happening inside the gun, right? So you have this little puck that you have in there, and then there's a voltage gap, and that's what accelerates the cloud away, right? And you can start gathering it from there and sending it through. Okay, now we're moving down the line a bit, sorry. So we're still in the injector, but we're looking at a couple different parts. Here, in the red, we have our weans. Now, our weans are what gives us 4 pi spin flipping capability in our machine. And so if you want a spin in this direction, cool, we'll set that up. If you want it over here, cool, we'll set that up. Now you're asking, but we don't know what the spin is by the end. Well, we do, right? We can calculate how that spin is going to process through the machine, and then we can kind of preload what spin comes out and then watch it process until it gets to the hull, which gives you the spin that you need at the end. So that is the beams right there. There's a couple of solenoids in there to help with the focusing as well. And then we come to the chopper. Get to the chopper. Sorry, I can't help but say that joke every single time. It's probably, if you're not a fan of Terminator, you don't get it. But anyway, or Predator. Anyway, so how does the chopper work? I'll get into that in a second, but we have these 2 cavities that kick the beam. And in the middle, we have this place that basically blocks most of the beam, right? Because we only want specific frequencies to get through so that we can extract properly to the hulls as needed. And so this is the inside of the chopper. As you can tell, these pictures are probably older than a lot of people in the room. It's what I had to work with, apologies. But that is the inside of the chopper. And you can also see kind of from the 2 different angles what you're looking at, right? How do they work? Well, you have your RF cavity, right? Oh, and this is automatically playing. Cool. So, all right, as it's going through, you'll notice that this is purple most of the time until it actually hits on one of the holes, right? So these 2 RF cavities, what they do is they kick the beam around in a circle, and it only gets through the slits that are corresponding to that hull. It's being sent around at a specific frequency so that that frequency is sampled at the right time, at the right place, so that you know which part of that beam is going to which hull. So that is what builds in our structure. And that's effectively how it works. It's a pretty cool basic system that no one understands unless they actually are shown this is how it works, right? So that's our chopper, and we're proud of it. A little bit about the beam structure as well. Oh, yeah.
I was just going to ask how it worked with Hall A and Hall D sharing a.
So the way that works is actually, so our fundamental frequency is 1497, right? Take a third of that. Take a third of that, and you get roughly 500, right? 499. But there's another trick when we added in that 4th hall, we then, okay, well, let's divide that up again. Let's do 250 or 247 or whatever it is, right? So 1500, 500, and then 250. And so then you're actually filling every other bucket.
Okay.
And so then one of them will go to, in this case, one of them will go to A, one of them will go to D. You can actually share with any of the other slits as well. It can get complicated at times because sometimes if you're sharing the wrong slit, then there's weird bleed through problems or different current issues. So there is careful planning that has to go into making sure this hall can accept, sharing with that slit and whatnot. But that was a good question. So I said that we are CW, continuous wave, right? We're filling all the buckets, the RF buckets. There is still a structure to it, right? It's never, nothing is ever purely continuous, right? So we have a wave structure, and this is just a quick definition of how we pulse our machine, right? So first off, you may hear, if you're ever in accounting houses, we're in tune mode, right? We had to switch to viewer limited. There's all these different modes. Tune mode is the one that the accelerator people need to be able to see what is actually happening. Because, for example, our beam position monitors, right? They are 4 little pickups that measure the beam charge centroid as it passes through. And as the charge centroid passes closer to some wires than others, you can do a difference over some and figure out where exactly that charge center is. Now, that gets complicated when you're in CW mode because all of a sudden in the Linax, where all of these beams are collinear, supposedly, it looks like a charge blob running through. And so you can't differentiate which beam is off center or which one is not. But if you go into tune mode, we have a pulse structure where you can see this little 4 microsecond pulse, and that tags each of the different lines that you can tell, the 4th pass beam is behaving properly, the 6th pass beam is not, or whatever. It usually goes the other way, actually. It's usually the lower passes that are more misbehaved. But that's why we have these 2 different beam structures. There's also viewer limited, which, if you have to put a screen in, you need to make sure you're not burning your screen, right? So we lower our intensity and we make it so we can actually put a viewer in and see what's happening in a transverse way. So that is the rough beam profile structure. So moving down towards the end, right, this is our booster. So this is our first kind of cryogenic-based accelerating part of our accelerator. It's still part of the injector. This is our new one, which is kind of cool because it combines if anyone used to come, you often hear our capture cavity versus our booster. Well, our new booster has both. So it has our little capture section here, and then it has the booster part there. And so it's all in one cryo module now. And this is effectively capturing and boosting, right? It's bringing it up to a moderate energy so that we can start accelerating the beam into the main accelerator. All right. It's a good aside to just mention what RF is, right? I like to just basically phrase this as the electrons are surfing on the wave through the machine, right? That's the easiest way to describe it. You have this RF wave that comes through in these structures. So this is, I believe, actually an ILC cavity, ILC, International Linear Collider, project that I wish would proceed, but probably will never. But we made a lot of their cavities here, prototype cavities here. But essentially, you have your electromagnetic fields. You can see, right-hand rule, it's going in and out. So you're accelerating that way. But that's essentially how these work. And I think when you take a tour, you're going to SRF, I believe, Institute. I'm not sure. But this is the rough part of it, right? Essentially, the RF is coming from the klystrons upstairs, down in, then your electrons are being accelerated on that wave. All right, moving slightly further downstream, we're walking. This is the next part of kind of the injector chain. So that's the end of the booster there. We have a couple of these dumps that we can use for diagnostics in the beginning. And then we have these little cryo modules here. Well, you'll notice this is actually a recirculating arc. And then this is the injector line, and we need to chicane it. Otherwise, it's going to be run into by the recirculating arcs. So there's a chicane in there as well. So this is, oh, look, there's yours truly, actually, right? That's me. You can get a good view of the size now, right? So I'm like 166 centimeters. So there you go. That's the size of everything. And this is the view kind of from where I'm standing there. If you turned around and walked down a little bit, that's what you'd be seeing. So this is the recirculating arc. And this is the injector line coming in. So the injector is back that way, coming this way. And that's where we're getting ready to come into the main machine. And we're walking. And you can see a couple of these pictures are a couple of years old. There's our old director, Stuart Henderson. So there's, but you can get an idea, like pretending we're in a tour, right? So anyway, this is, again, kind of at the end there. You can see quadrupole magnet here, some diagnostics. I'll take a quick aside real quick. Because you're seeing that and you're seeing these blue dipoles over there. So in an accelerator, dipoles are used to change the trajectory of a beam. So they are linear magnets. So they either kick up and down or left and right, unless you are a glutton for punishment and you want to put one in and skew, and then you could do a diagonal. But we really try to avoid the diagonals if we can. So dipoles are for steering and bending. Quadrupoles are effectively lenses, right? They focus and defocus. Now, the big difference from regular regular light optics is that a focusing lens in light optics focuses, right? But in beam optics, it focuses in one plane and defocuses in the other. And so if you have a horizontal focusing quadrupole, then it is vertically defocusing and vice versa. So when you set these up, you have to kind of alternate them. There are different ways to alternate them. It doesn't have to be what we call a photo lattice, which is focus, drift, defocus, drift. So the O's are actually zeros. Anyway, focus, defocus. You can also do doublets, triplets, and all these different combinations to really control the beam dynamics so that you're getting what you want them to be at whatever target you have. So that's basically how, and our machine is only linear magnets. We have only dipoles and quadrupoles in CEBAF. A long time ago, they installed sextupoles and then decided that they were not worth the trouble because whatever errors that we had that we needed to correct with them were not great enough to need them. So while they are still installed in the tunnel, they are not plugged in. There's no power to them. You can still see the remnants of them. They look little orange things. You might see some in some of the slides. But the sextupoles are used for higher orders. Now, nominally, I say we don't have any, but real magnets have higher order terms, right? So as you make them and you do your expansions, you'll see, okay, there is a sextupole term in this one. We do have some magnets that have more significant non-compensate for them as well, without adding actual sextupoles and octupoles, etc. Now we're coming to a recombiner. I'm going to come back to this point in a minute, so hang on for me. But one of the main things at our machine that's different than a ring, in rings, you recircle many times around in the same set of magnets, right? In our machine, I like to liken this to water in a hose. So when you have a higher energy beam, it's akin to higher pressure water in a hose, right? The higher the energy, the higher momentum, the more rigid the beam becomes. And so if you're trying to bend several different hoses of water at the same time, so imagine you have a hose in your hand and it's low pressure water. You stick your thumb on the end and you can stop it or you can redirect it easily, right? If it's high pressure water, you got to put a little more force into that thumb to be able to stop that water or bend it, right? Same idea with our beam. The more energetic the beam, the more rigid it becomes. And so if you try to bend the same beams with the same magnets, you can do it with certain circumstances, but for us, we actually separated them out so that the lowest energy beams are bent the same amount as the highest energy beams. Now, you can only do that by using different magnets of different strengths and sizes. And so once we get to the arc, I'll point those out. But that is a crucial difference between our machine and other machines. Because we're recirculating in that way, we have to separate out our beams and then recombine them for linear propagation. So again, you're in a tour, right? So there's people in front of you, and I can't, I have to apologize, but this is where our spectrometer dump would normally be. This is kind of the beginning of the recombiner area. So the beams are all the lowest energies at the top and the highest energies at the bottom. And you can notice the size differences. So the magnets up here are much smaller than the magnets down here. That one's even smaller yet. That's the idea. You'll also notice, for example, a single quad doublet, right? And up here, there's just single quads. You don't need as many of the magnets to control the smaller energy or the lower energy beam. Let's move into the actual LINAC proper. Again, if you have questions, don't hesitate to reach out and interrupt me. LINAC proper. So this is kind of an interesting point. So we're coming in with the recirculated beams here, right, through those recombiners. But then back here, it's hard to see, but there's this little blue rectangle. That's actually a small chicane dipole from the injector line. So it's coming in at 123 MeV. That changes depending on if we're having different setups, but nominally, nominal machine, 123 MeV coming in. And underneath this table is a small dipole where the two beams then co-propagate. And so you have all these high energy beams and then the new injected beam coming in at the same spot, entering at a point right here, and it's coming through. These are vacuum pumps. And then as we move down, they will then progress down through the LINACs, right? So this is halfway down. So we were there, now we've moved down a bit, and this is to give you an idea, right? So all of these waveguides are carrying that RF wave from the klystrons upstairs down into the LINACs and providing the RF wave for the electrons to surf on. Moving down, so the beam is coming this way and then it's going down that way. We have different types of cryomodules, right? They made the decision to name them after nominal energy that you get for each one, but it's not actually really what we get out of them. So for example, a C100 cavity was supposed to have 100 MeV per cryomodule, but it didn't turn out that way. It's a little lower than that. We have C75, C50, C25s in various places around the machine. But the goal is to get about 1 GeV per LINAC nominally, right? A little bit more than 1 GeV per LINAC. So if you go around one pass and you get one pass beam, you get 2 GeV beam roughly, right, at your hull. If you go around again, yeah, you double it, right? And so every time you go around, you get basically an order of 2 GeV every pass. So that's the idea of how we set them up. Now, right now, some of you may be aware, we are running a very special energy setup where, well, it's very, very low energy, and a whole lot of our cryo modules have actually been turned off. And I mean, extremely low energy right now, and it's actually been really hard because, as I mentioned, the lower the energy beam, the less rigidity it is. And so if you have a machine that's designed for something far greater in energy, being able to have that fine touch to control a very, what I like to call floppy beam is difficult, right? And so that is, some of you may be aware that we've been struggling to deliver sometimes, and it is because we're running at a lower energy now than we have run even, I think, in the 6th-gen era. So, yeah.
So you guys are basically trying to crack an egg with a hydraulic press?
Yes, that's a really good analogy. Yeah, crack an egg with a hydraulic press. I like it. That is, yeah, yeah, nice and gentle. Oops, too far, right? It's gentle hands, right? Artist touch, artist touch. So, all right, we're going to move down the Linac a little more, and then we're going to get to the spreader. Now, the spreader is a complicated beast. I'll go back to this first, actually. This is called a common dipole. So this acts like a Pink Floyd album cover, I mean, a prism, right? And so what happens is you have the beam coming in from the left, entering there, and all of the different energies are there at the same time. Now, like I said, if you try to use the same magnets to bend different energy beams, they're not going to bend it the same way. Well, in this case, we're using that to our advantage, right? So the lowest energy beam is the least rigid, is the most floppy, right? So it gets kicked up the highest. It's easiest to kick up. And so this is our first pass beam coming up. And then the second pass actually makes it to the second BCOM. So this one, it looks like it's making it through there. I assure you, it's not in the coils. It was just an upgrade, and so it's actually going through the return steel. And yes, that causes nonlinearities and issues, but we correct for them. So the first pass beam bypasses the main part of this magnet and just moves up here. Pass 2, 3, 4, and 5 are here. And then you'll see they come back down. And then there's actually the whole D line as well, because we're in the northeast corner. So there's 6 passes here, but one of them is going directly to Hull D, and the other ones are either destined for the hulls or recirculation further. To show you what these actually look like, so this is the end of the cryo module, right? This is the last cryo module in the North Linac. This is a quadrupole here to get you one last spot to focus before you go into everything. Just as an aside, this is an NDX detector. This detects radiation, so neutrons and gamma together. There's 2 pickups, so that way we can see what sort of levels of radiation are coming out of these cryo modules, which is very non-trivial amounts of radiation are coming out of these cryo modules. So then the beam progresses through, gets focused, there's a pumping station, and then it goes into these BCOMs, right? And like I said, pass 1, you see it's not in the coil, it's just outside of the coil, going through the return steel, and all the other passes are going through. And then there's a recombiner on the other side, and we purposely make these mirror symmetric. So if you split one way, you unsplit exactly the opposite. And that helps you get rid of chromaticity problems and make the beam nice, so to speak, right? So that is why we do that. And you can see kind of, it is an exact front and back of each other. We have spreaders on the upstream end of our arcs and recombiners on the downstream end of the arcs, or near the hulls if there's extracting as well. So east spreader, oh, I forgot to mention another key part, sorry. So the other part of this, you might notice it's 2 steps, 1 and then 2. 1, 2, 1, 2. We do that on purpose, and that is to control the beam dynamics itself, right? So whenever you bend a beam, you get what's called dispersion. And if you bend it too much, you get more dispersion. You don't really want to transport dispersion. And so when you do this first step, you'll then have, there's a quadrupole here, a quadrupole here, and a quadrupole here. And what you do is the 2 outer quadrupoles are used to correct your dispersion, right? So once you have the dispersion, you can crank them up, flip the sign of the dispersion so it's going the other way. And as it's flipping, it crosses a midpoint. That midpoint is where we put that other quadrupole, right? So at the 0 crossing where there is no dispersion, there's dispersion prime, but no dispersion. You actually then set something to control your beta function so that your beam size doesn't blow up. So that gets cranked down again. And then you kick it again with that last one to get your dispersion coming back up. And then as you enter here, you get one more. And then here, you close all your dispersion and you have a nice achromatic step. So that is why they have 2 steps in between. Now, another interesting point that people tend to not know, the ratio of this position to that position to that position of those quads is directly related to the step sizes between.
You get similar dispersion issues when you go around like the arc itself on like the horizontal plane as well. And is there a similar like step situation, or is that just controlled with various like quadrupoles and things like that?
That's a great question. So we do get dispersion in our arcs, but we purposely make it so that the net arc is achromatic.
Oh,
Right,
okay.
and so we compensate for it with quads, with optics changes, with, whatnot. But yeah, that was a great question because it does work in both planes, right? And so if you look at, I don't have any optics plots in here, but if you look at the optics, at some point you can write to me and I'll send you some optics.
Okay, sure.
Just to show like they have a really cool repeating pattern of like, here's what the dispersion does, right? And then it cancels by the end. So good question. All right. Going into the arc, or this is still the spreader. This is an overhead view up top, and this is from the side. And here's our dog legs. Silly name for an important function. So one of the other issues we have with this machine, some of you may have noticed that our temperature varies widely in Virginia, going from I need a hoodie to I need to be in a pool right now within a day. And so this also wreaks havoc on our machine. A temperature-based expansion, thermal expansion, is a real thing, and it affects us throughout the day. And so these dog leg magnets that you have here are actually used to compensate for the path length difference as you exit one linac and then go around that arc and come into the next linac. You need to make sure that all of a sudden you're not on the wrong part of that RF wave, right? You still need to stay on the same spot to be accelerating. If your path length changes in between, right, all of a sudden you're no longer on that right accelerating part of the RF wave, you might end up decelerating. You may end up getting a bigger energy spread, right? And so we have these dogleg magnets, which essentially bends the beam a little bit and then bends it back. And we change the amount that it's bent depending on what path length adjustment is needed to get around and be back on the right part of that RF wave. And that's usually adjusted a couple times a day. And then throughout the year, I think there's the equivalent of several centimeters of adjustment needed throughout the year, which is, it sounds like nothing, but being that we are sub-millimeter precision on our RF wave, centimeters matter a lot. So those are our dog legs. This is the arc. Again, you have an overhead view just so you can see. And then you have just the straight ahead. Also, you'll notice the kind of interesting pattern, right? So these are our big dipoles, bigger on the bottom, smaller on top. They're all placed kind of around the same place, both due to optics, but also due to being able to access and fix these things. And so we do have them all spread out. We have our quadrupoles kind of in these areas, diagnostic spread out, but you'll notice these nice little kind of almost arch patterns going through the arcs as they go. And this is allowing us to give the bends that we need at the right places to then use the optics to both control the size of the beam, how it's converging, diverging, and the dispersion as well as we go through. And so these are the arcs. And so here is a nice view. Here's a couple quadrupoles. This is a beam position monitor here. It's a little hard to see maybe, but I think the slides are online. You can get a better view of the actual photo, I think. But this is a beam position monitor right by a quadrupole. And then you see this little blue one, that's a corrector dipole, right? So we always like to assume nominal in physics, right? Everything is a spherical cow in a vacuum. But the reality is nothing is ever really nominal. And so you need to have these corrector magnets to say, my orbit's a little off, right? How do I know it's off? Well, I know it's off because I'm reading it in that beam position monitor that I was telling you about earlier. So I know that the charge center is not actually in the center. And so I give it a little kick horizontally or vertically, depending on which girder we're at. So you read it, you change it. You can also adjust the quads if you need to. You can see that wonderful little orange thing there that I had mentioned. That is one of our unplugged sextupoles. So there you go. They exist. You've seen them virtually. Never shall they be spoken of again. And then we have our dipole magnets coming through. And so that's the idea. And that's giving you your view of where you are. So this is kind of in the beginning of the east arc, and you can see it coming through. As another heads up, from this wall to the other wall is a little over 3 meters, right? Let's say 3.5-ish meters or something like that. It's a relatively tight space. And so it's interesting trying to transport heavy equipment like cryomodules or these gigantic dipoles through these very tight spaces. We have interesting side loading forklifts and whatnot so that you could drive through and just put it right in. This is another reason why some people sometimes ask, why do we not make these arcs all different sizes instead? One of them is ease of access, right? If you need to maintain a machine, it's easier to have everything accessible in one spot and not have to disassemble everything to get to the next one. And so that's part of the reason why these are stacked. It saves real estate, saves maintenance costs and efforts as well. So moving down, this is now going to be, anyone here working Hall D? There we go. This is going to be your special part. All right, so you'll notice as we come out, so this is a side view here, and then there's these 2 big dipoles, 1, 2, and it goes up the ramp to Hall D. When they upgraded this, it's interesting. I don't know if you can see it in the picture, but you'll notice that that edge of that magnet's actually a little bit below the concrete. They actually had to dig out a little section of concrete to make that magnet fit when they upgraded for Hall D. So it's just a little interesting tidbit. So yeah, the Hall D line's coming this way and the recirculation is continuing this way. So here you go. There's a couple people by those large dipoles. I don't think you can see it, but it is embedded a little bit in the concrete there and it comes up. You're looking down. So the beam is coming in this direction here to Hall D. But that is where the trip and the journey starts going to Hall D. Now, we skipped a lot of the east arc because you saw it coming around. You'll notice the pattern is persisting, and then we get to the recombiner. We spoke about recombiners. Mirror symmetric to the other one. Another interesting tidbit is that these recombiners had to be redesigned for the 12 GeV. If you think about this, you think, okay, it shouldn't be a big deal. You just spread the things, but it matters what your injection energy is as well, because the ratio of these heights will change depending on the energy that's coming into them, right? And so if all of a sudden you're keeping your injection energy the same, but changing your LINAC energy, that ratio is going to be different coming through them, and then your heights are wrong. So you have to be very careful. If we scale the energy in the LINACs, we also have to scale it in the injector end. LINAC, more LINAC. There we go. So coming down, this is from the end of the south LINAC. I'm going to answer the question before it comes. Yes, those are burlap sacks. Yes, they are an interesting low-tech solution for a high-tech problem. They are essentially filled with these special little beads. But let's call it sand, because that's essentially what they are, sandbags. And it turns out that we had an issue with microphonics. Microphonics are coming from vibrations in some of the equipment that is on top of those cryomodules. And so while we are trying to repair this problem, and some of those sandbags are now gone, it is an incremental step. And so in the meantime, they figure, well, they're vibrating. Why don't we dampen them with burlap sacks full of sand, basically? And so, yes, there are sandbags in the tunnel and they are helping. So I had to answer that one. During the last open house, that was actually one of my most frequent questions, because I was stationed at this spreader. Instead of asking me how the spreader works, everyone's like, what are the sandbags for? So I'm nipping that one in the bud right now. So anyway, we're coming into the spreader now. So we're coming out again. You have another NDX, pumping station, diagnostics, and then you're coming through that common dipole again into the west spreader. Same deal as the east, slightly different because the energy is slightly higher because you've gone through one more LINAC, but it's the same idea, same concept. Skipping through. So then, yep. I just wanted to show some better pictures of the spreader as well. So this here is actually not a regular dipole. That is a septum magnet. And so you'll see, for example, this one, so pass 1, 2, 3, 4, and 5 are both in here. And as it comes out, 5 will pass through there, and then, or sorry, 4 will pass through there, and 5 goes through there. You'll notice there's some really, really tight clearances in our machine. Yes, there are. And yes, those magnets do crosstalk. And so one of the interesting things that we get from external people all the time is how do you deal with crosstalk, right? Like if you design something and all of a sudden you're seeing these beam lines that are all close together, how do you deal with that? It's more of an operational issue than anything. So if you know that this exists and you know you're going to have these fringe fields coming into other parts of your machine, what you do is you just turn on all the magnets from the beginning, right? And that way, whatever's in there is already in there. So as you start threading your beam around, we don't get to just flip a switch and turn on the machine. I invite any of you to come sit in the control room for a day and see the hair pulling that happens trying to maintain our beam in the pipe itself. We do an amazing job, but it's hard, right? And so as we thread the beam through, especially when we're first turning on after being down for a long time, it takes a lot of effort to make sure like, okay, the model says this. Yeah, but the model doesn't include the magnetic contribution from here or, you know, the slight offset that you had at the beam down there. And so there's a whole lot of, okay, let's turn it to what the model says, you know, set our magnets to what the model says. Okay, where's the beam, right? Oh, it's stuck here. All right, now we adjust that. Okay, it's moving up a little bit. Good, 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 right? And there's a lot of kind of like testing and seeing and like, okay, send in the diagnostics, send in the viewer, send in this and see what's actually happening, right? And then we adjust it and then we basically do a zero pause, right? Like this is the setting, this works, nobody touch it, save it, right? Now we say that. Also, the reality is this machine is 40 years old, and sometimes you set it and it says, I'm not staying set, right? And something will change, right? We'll get a power surge, we'll get a hiccup, like someone will sneeze funny in the control center, and all of a sudden, like something drifts and we don't know what. And the whole machine just has to kind of be retuned again, right? There's also issues with hysteresis. So for example, these are all iron core magnets for the most part. If you don't go through their hysteresis cycle occasionally, then they're not reproducible, right? So a few weeks ago, this is a good example. They were forced to send a stack of magnets through a hysteresis cycle because a power supply went out. And when it came back on, you can't just send beam again. You have to cycle your magnets through the hysteresis cycle. So when we do that, that's great, except for now the set point is slightly different and the beam is no longer where it was. And we have to go figure out where the beam is again. And of course you check the model and it's not actually where the model says it is. It's slightly different. It's very experimental. It's really fun and frustrating, but fun. So, but anyway, that was a bit of an aside to explain. So septum magnets themselves also introduce more nonlinearities, right? So while they're useful for separating the beams out or putting them back together, you do then have to worry about the level of nonlinearities that are being introduced into it. And that is one of the complicated parts of it. So moving up a little more, you see the second step. You'll notice that a couple of these magnets that are supposed to be rectangles don't look much like rectangles anymore. That is by design, supposedly, because it was so tight and the clearances were so very tight, they actually needed to bend those rectangular magnets a bit, and they work fine. They're modeled properly, nominally. And yeah, so they work, but it is very tight clearances, right? And so you do have to worry about, you know, this dipole impacting this empty space in between the dipole and the quadrupole. These are concerns that you have to deal with. Now, we have diagnostics, but it's harder here, right? So you can see one beam position monitor right here. You can see one here and one here. But there's not a lot of diagnostics in these areas because, for example, the beam pipe on these diagonals is sag, right? So even if you put a beam position monitor on there, it's not like the rest of the machine, which has like very strict tolerances on how close everything has to be and how well measured. If your beam pipe is sagging a bit more one day than another because of thermal expansion differences, you no longer know if you're in the center or if you're off center, or if you're supposed to be off center because the beam position monitor is not centered, right? And so we don't have a lot of diagnostics in those areas, which also complicates getting through the corners, so to speak. Coming on through, we're in the west spreader still. There's me again, and actually Ben Schomloffel, who put these slides together. That's Ben right there. So yeah, make sure you give him big props as well. So as we're coming through, here's a nice view of a bunch of quadrupoles actually. So you'll notice it's always quadrupole corrector, right? Beam position monitor, quadrupole corrector, monitor, quadrupole corrector, monitor, quadrupole corrector. We have to remember that when we're doing this, because if we're measuring something and we don't remember the order, oh, is this before or after that quad, right? Then you might be trying to, and this is it's not listed easily, right? You don't necessarily know where these are unless you were doing this all the time, right? So if you think that the order is different and that you have a quadrupole beam position monitor corrector, or that the BPM is after the correctors, you might start trying to adjust things in the wrong spot, right? And so you have to remember beam position monitor, quadrupole corrector in the arcs. And you'll notice also that there's more of them at these the higher energies, lower arcs. Again, more rigid beam, you need more oomph to control it. Yeah.
I've noticed in some of the schematics, there's that box with the X through it labeled crossover at the bottom to there. What's that about?
So there's only so there's certain places, sometimes you have to get behind the beam line, right? And you can't let people just kind of sit on the actual bare beam pipe. So there's certain areas where they've reinforced it to where it's kind of like wrestling, where you got to go through the ropes, right? That's where the crossovers are.
Oh,
Those are specifically crossover points.
Got it. All right.
Yeah.
So that's just for access. That isn't
Yeah.
to do with.
Yeah, there's about a meter and a half behind the beam line where you need like all the wiring and cabling is back there, access to a bunch of the electronics is back there. So you do need a place to be able to go. And that's where those are. Good question. Yep. Right. West extraction. So the extraction is super fun. You'll see that there's more and more of these, but these are our RF kickers basically. So this is, again, is an overhead view on the top. And this is the side view. So you have a single one here, 2, 2, 3, 4. These are RF kickers. These are how we extract our beam. And this is a really complicated and unique system. I'm going to try to give you the most basic version of it because it's complicated and I'm probably going to mess up the more complicated version of it. So the way we extract is, again, these are actually what they look like. I'll step back. So this is actually what they look like. They're radio frequency based kicks. And what they do is they give a very quick beam transverse kick to the beam that you want to extract. And then the beam you don't want to extract, you no longer kick. And so, for example, we mentioned in the beginning the chopper, right? And the different slits, A, B, C, right? We want to make sure that if A wants a specific beam, let's say pass 1, then as it's coming through, we know, okay, this is A, kick it and then stop kicking. And it gives it a little transverse kick. And then that progresses down actually through an offset quadrupole, then samples the dipole part of that quadrupole and gives it more of a kick. And then it goes through a series of dipoles and septa and extracts towards the beam, towards the hulls. Now, the part that's not kicked just continues through and is allowed to recirculate more. Those are the dog legs on the other side. And this is the extraction. So this here is also a septum, right? So the recirculating beam is following this very outer part here, right? But the part that's going to the hulls, you can barely see the difference. There is another beam line that goes right there, right? So the RF kicker gives this tiny little kick, and then we start magnetically pushing the rest of it away. But that takes space, right? So there's a lot of space to get this all the way extracted. So it comes through, it's very tight in there as well. Excuse me. And so here's the extraction again. This is sort of more of the schematic on what's happening, right? So you have the RF separators, dog legs. You have viewers there, because this is also an interesting spot where they're often the recirculating and the extracted beam are sharing the same vacuum chamber. And you need to know which one is going where. So you put in a viewer, and the viewer will say, like, there's these 2 little wires on the viewer, and you want to make sure extracted beam is close to this wire, and you want to make sure that the recirculating beam is closer to this wire, right? And so you visually inspect, is this close to where it should be before we continue, right? And then it continues through, you go through these septa. Oh, okay. And this is kind of the schematic. So I'm going to let it kind of play through. Oh, this one doesn't automatically play. Okay. We discussed the fundamental frequency, and then the beam is coming that way. So let's go through. We have A, B, and C on different parts of these pulses, right? Now, we want to, some of those beams are going to the hull, some are going to be recirculated. And we turn on our separator cavity at 1/3 of the fundamental frequency. And, excuse me, and as we turn them on, let's say we're, in this case, we're sending hull B beam and we're recirculating A and C. So that will separate it out. So you're getting the kicks only on the hull B, and then the A and C can continue recirculating. Then it has to go through a vertical separator, which goes through a Lambertson special septum called a Lambertson. It has one kick this way, one kick this way, and one no field. So it's 3 separate field directions in one magnet. It's brilliant. You can't tell by looking at it from the outside unless you know what you're looking for, but it's a really cool magnet. Now we have this 5th pass problem where we only have the 3 slits, so we have to do the 4 holes. And so how do we deal with this, right? So we send this, the 5th pass goes through the vertical separator at half the fundamental frequency. So you have the 500 and the 750, right? That gives you an offset. So now you're filling every other bucket. And I'm trying to speed this up a little bit. And that is really taking its time. There we go. So you fill every other bucket with D. There we go. I borrowed these slides, I'm sorry. And so there you go. And that's how you can send to D separately. Oh my goodness. Okay, there's more. There's more. Okay, there it is. Okay, so we have, of course, a recombiner in the transport switchyard as well. It's identical. These are some of those also tight tolerances. So you see there's one magnet and there's a different magnet. And there's the beam line, right? So those are a few centimeters apart. Again, fringe fields, but as long as you're operationally careful, you can make it happen. There's Sean walking down towards the halls. This is the recirculating arc, and that is the hall line there. And come on, there we go. There's our RF kickers and our recombiner, more recombiner. This is towards the transport end. And then we have our hall lines. So our Lambertson is here, separates them out. You have A, B, and C. There's the Lambertson. It doesn't look like much, but I promise you it's one of the coolest magnets you'll ever hear about, even if it doesn't always behave as it should. This is kind of how it comes. So the beam is coming in this direction. That's the Lambertson. So you see A, B, and C. They're not at the same height. They're all kicked slightly differently due to the Lambertson. And then again, you have A, B, and C. And there we go. More transport. You can see where you're looking. I'm speeding up a little bit because we're at the end of my. Okay. But essentially, yeah. So you're going this way to A, B down the middle, C down that way, and you have these transport lines. There's also an old beam dump that I wish we still use, but we don't anymore. It was really useful. It's attached to the C line, and we used to be able to use that for full power tests, basically. Strip the C line, C beam away right into the dump, but it's no longer active, and it hasn't been rated for our current energies. So if we ever do want to bring it back, it will require concerted effort and financial support. But here's a little bit more. So you get some of your dumplets in here. You have your optics. Again, the sextipoles that are not sextipoles. And then you can see again, A, B, and C. And this is standing so that A is to the right, B is right up the middle, and C. And following A, just as an example, there's Ben again at the end. And there's our brilliant way to stop backscattering back into the beam line. Steve Sewering came up with this idea of, well, we need to plug this hole. Welding rods will do it. And there you go. You got a bunch of welding rods stuffed around the beam pipe to stop backscattering into the accelerator from the hall. And I think that's everything. Yeah. Questions?
Yeah, I want to ask about, I know you mentioned this a little bit, but what all went into the 12 JEV upgrade? And then as like a follow-up question to this, what is for like a hypothetical 22 JEV upgrade? What is going to need to happen? Did they add like a?
Oh, man.
Was this,
Oh, I'm being recorded right now. Yeah, okay. So a lot had to go into the 12 JEV, right? We had to upgrade all of our magnets. We had to add an entire arc in the west side.
Okay, yeah.
We had to change our spreaders and recombiners. We installed a bunch of new C100s so to get the extra acceleration power, right? We added Hall D. That didn't exist prior to 12 JEV. Now, as far as higher energy, this is, of course, complicated question. So looking at higher energies, there's different schools of thought on how to achieve this. There has been a project that is looking at something called an FFA, right? An FFA is a fixed field alternating gradient accelerator. Now, what these use are fixed field magnets. They can be permanent, they can be non-permanent magnets, but they have to be a fixed field that allow for multiple beam energies to go through at the same time. Now, these have existed up to maybe 200, maybe 300 MeV. Now, trying to do something at that scale, at the GeV scale, has never been done. Now, they are looking into that, right? It is an option that they're looking into here, but it is a complicated, it ends up being a very complicated process that we're unsure yet. There's still feasibility issues that we're checking into, right? But that is not to say that there are not other methods to get to higher energies, right? I mentioned earlier that we have a very old machine, right? I mean, yesterday, I'm wearing the wrong shirt today. Yesterday, I was wearing the 40th anniversary shirt, right? So the machine is 40 years old. There's components in the machine that are original, right? Now, to me, upgrades are great, but at some level, you also should probably look at your foundation, right? If you have a car, let's say you have a car from the mid-'80s. I just picked that date at random, right? Let's say you have a nice hot rod from the mid-'80s, and it's got some engine problems, right? But you slap some new tires on it, you slap some paint on it, and it looks great, right? But you still can't really gun it because it's got those engine problems, right? But if you take the time to actually go through and say, hey, what's wrong with the engine? Let's look at this, let's repair this, let's improve this, right? And then you add in all the other bells and whistles, then you get a nice car again, right? So that's kind of another school of thought as to how future upgrades might be more achievable.
Thanks, Ryan.
Yeah.
Any other questions?
Hi, so my question is like a bit dummy question. So are we generating different energy, like a initial from the beam from the injector, or I mean like at the same time, can we like generate like different energy from the injector itself?
So the injector provides the electrons, and then the machine, CEBAF, the energy is provided by those RF cavities. And so you can only use, like, for example, right now we have the Linacs set at a different setting than they normally are, but you have to set the Linacs at a specific setting for kind of all of the beams. And the only way that the halls can see different energies is by splitting that beam off earlier, So there's a top energy, and then you can get essentially number of passes lower than that, right? So nominally, it's 2 GeV per pass roughly. And so if you want the whole 12 or 10 or 8, you could do that, right? And if we have special settings, then you could do the in-betweens. Does that make sense?
More questions? Seems not the case. Thanks a lot again for all the time. Okay, great.
This was a special one because on Friday we will not go in the tunnel. So that was your only chance in the near future to see that. So thank you, Ryan, again.